Right, let's continue. Here, what did we learn actually last week? We learned the system, right? Especially for the system, and we have how many system properties have we learned? 6, right? Memoryless, invertibility, causality, stability, time invariance, and linearity. And in this course, we only focus on the LTI system, which is linear time invariant system. Here we have an example. If I have a system, okay, that is a unit step function, and I have an input, well, what is our output? Because this is the LTI system, we assume this is an LTI system. So the output will be the convolution of your input and your system. Okay, so here we have a convolution. We will talk more about the convolution today. So here's the formula for the convolution. Xk here, it should be 2 to the k u to the k u of k times u n minus k. So first we need to find out this product. So what is the uk and un minus k? Let's have here. So what is u of k? Okay, suppose u of k is here. U is a unit step function, right? So I should have this is unit step function. Our domain variable right now is k. And how about u minus k? If I have a minus, I flip this axis. So I got, and then how about u m minus k? I shift. This time there's still 0. And then m minus k, m minus k, which means minus k plus n. I shift n to the right or to the left. If I reverse this, then plus n, that means my signal is shifting to the right by n unit. Okay, so suppose this is u m minus k. Okay, so now you can see that clearly when u of k times u m minus k, what is the result? This and this. I may only have this part, right? So it should be still u m minus k, but now the k is from 0 to infinity. Okay, starting from 0. And that also means that if my n is less than k, okay, then this will be here. 0 is here. So when I do the, so that will be 0. Or we'll see, we talk about that later. So any questions so far for expressing the y? Okay, so now my k should be from 0 to infinity. So when n is less than 0, say minus 5. So there'll be minus k minus 5. In this case, minus k minus 5, u of this unit step function, I only have a values when k is greater than 0. This k is greater than 0. Okay, and then if I have n less than 0, okay, n less than 0, but we know that k is always greater than 0. So k is greater than n. Okay. So overall, when k is greater than n, and this is negative, right? When it is negative, let's see the unit step function, the definition of it. When here that's less than 0, the value is 0. Okay, only when n is greater than 0, that's 1. Overall here is greater than 0, that'll be 1. Otherwise it is 0. Now, overall, this is less than 0. So the answer is 0. Okay? And when n is greater than 0, and I do have values, right? I do have values here. And this value is not from 0 to infinity, it's only from 0 to n. Okay, so for example, 5 minus k. So 1, 2, 3, 4, here's 5. It looks like this. Okay. And then k is greater than 0, so I only have values here. Alright, any questions for this one? Alright, so now this is the discrete case. Now let's see the continuous time, linear time invariant systems. For the continuous time, the output is input convolve your system. And there will be x tau h t minus tau d tau. Okay, and what is ht here? So if we don't know the system, if we don't know the system, actually we can just send the impulse, the unit impulse. Once we send the unit impulse, then we get the system response. And for the continuous time signal, actually for your signal, we can write the signal as your value times the impulse signal, the shifted impulse signal. Okay, that means the signal looks like this. Alright, anyway, if I shift every time I got a value, okay, we got the value, and then when you integrate that, you get the the continuous signal. Okay, and then for this shifted impulse, unit impulse, it's like this. If I shift it by t, then I should have what's the, let's see, okay, let's say green. So I shift by t, and since the system is linear, so we can write your output here, and then this h tau is the system's response. This system responds to your shifted impulse. And then the system is time invariant. What does that mean, time invariant? That means what is h tau of t? That means I shift by tau, which means if I have a signal, well, say impulse, this impulse is sent to the system. And then suppose the output is system response h. If I shift by tau, then the output is also shifted by tau. So here I shift by tau, and I write it down, the t minus tau as h tau of t. So the output is x tau h t minus tau d tau, and is x convolve your system response. Let's just see an example. My system is a unit step function, and then I want to find the system's response. My input is here. So the output is input in convolve your system. That is x tau times h t minus tau d tau. Okay, here we have x, that's e to the minus tau u of tau, and then your h is u t minus tau d tau. Again, we need to deal with this term. So let's see. Here is 0, and what is u of tau? The unit step function u of tau. And what is the u of minus tau? Here is still 0. So I do the reverse. This is u minus tau. So if I shift by t, minus tau plus t, what does it look like? Here's 0, and here's t. This is minus tau plus t. Okay, I shift by t. So these two, I only have a value from 0 to infinity. Okay, but that is u minus tau plus t. Okay, here. If t is less than 0, then nothing, right? Y will be 0. Okay, so here, that is e to the minus tau u of t minus tau d tau, and the tau is from 0 to infinity. Let's see this one. When t is greater than 0, okay, when t is greater than 0, we have value. When t is less than 0, okay, these two, we can say that there's just 0. Okay. So first, case 1. When t is greater than 0, the y is from 0 to t at e to the minus tau d tau. Okay, now the tau is, this tau is from zero, well, tau is from 0 to infinity, and the t is greater than 0. And the other case, when t is less than 0, the output is 0. So overall, that is 1 minus e to the minus t. We can have a unit step function. You can observe this. My input is a unit step function. Oh, a part of a unit step function times something. Okay? And then observe your output. Also for discrete time case, this is my input. And what is my output? I can also write it on this as, okay, for LTI system. Just keep in mind that what you observed so far. Now let's look into the convolution. Okay, we have discrete time convolution and also continuous time convolution. First, let's have the graphical interpretation of the discrete time convolution. So for the convolution, you know the formula like is this. I have two signals. You can think about these two signals. Okay, what do they do for this? The dummy variable now is like k. So here you can see that the steps are, first, the dummy variable is k, so first I flip. So here, minus means I flip it. Flip. And then, remember, your dummy variable is k. Okay, and then what is n? N means shift. I flip and then I shift. And then you times xk. Okay, here you multiply. And finally, you do the summation. So, first we flip h of k about k equals 0. So here we have h minus k. And then you shift to the right by n if n is greater than 0, or left if n is less than 0. Okay, so you shift, then you do the point-wise multiply. So this h times hk, then you get xk times h m minus k. And finally, you sum the product. Okay, you have a lot of this term. Then you sum the product. Okay. You flip first, and then you shift, then you multiply. Finally, you do the sum up. Okay. Let's see an example. So suppose I have a signal, or you can think about this as an input. So this is xn. So my input minus 1, 0, 1, 2, and 3. Okay, and I have 1/2, and here we have 1, so 3/2. So this is 1/2, here's 1, and 3/2. That's our signal. And then for the system, let me finish that, you can plot. So for your system, -1, 0, 1, 2, 3. They're all 1 from 0 to 3 to 2. Okay, they are 1. Now first, for n is less than 0, first we need to flip. Okay, so when we flip, I will get here, right? And when n is less than 0, that means I shift to the left. So I will get what? Oh, it should be n here. Now it is k-axis. And this is h m minus k, and n is less than 0. So my here, suppose this is n, here's n minus 1, n minus 2. I think maybe this is better to move to here. So we flipped and also shift. Next we need to do the pointwise multiply, but by xk. So we need to redraw this to k rather than n. So actually I can just copy. And now I need to change this to actually k. So when I do the multiplication, what is the output? The product is 0, right? There's no overlap. So xk times h n minus k is 0 whenever n is less than 0 for all k. So your result, here's your final result, your y, that'll be 0. So I flipped and then shift the n to the left, and then I will moving forward to the right. So we'll move to the right. So there'll be 0, 0, 0 until when n is 0. When n is 0, that means I just flip. Okay, so my x minus k, h minus k will be here, here, here. So first, let's see when n equals 0. When n is 0, let's see the k, the h. So here, I want to plot the h, m minus k. So 0 minus k, 1, 2, 0, minus 1, minus 2, minus 3. I have 1, 1, and then xk. Oh, so when I do the multiplication, we get 1/2, right? So here we have 1/2. Let's have a blue as your output. Here 1/2, and then this is xk times h 0 minus k. So here the sum over k, we get y at 0, that's 1/2. When n equals 1, so I will shift this to the right for another 1 unit. Okay, I need to redraw. Here we have h1 minus k, right? And your x is still the same. Now put here. Okay, and then what is your output? You do the multiplication, right? Here we have value, here we have a value. So at 0 we have 1/2. At 1 we have 1. So this is x of k times h1 minus k. And we have 1/2 and 1. So if you do the sum over k, you have y1, that's 3 over 2. Now we shift to 1. Next, we need to shift one more step. So when n equals 2, when n equals 2, then your h2 minus k becomes, here's your k. This is h2 minus k. So we get 1, 1, and 1. And then your x, same, so let's copy it. Right, so when you do the multiplication, 1/2, 1, and 3 over 2. So your output, here you have 1/2. And this you have 1 and 3 over 2. This is 1/2, 1, and 3 over 2. And this is the output of xk times h2 minus k. So you need to sum over k. And then you get y2 equals 3. Right. 1/2 plus 1 plus 3 over 2. You get 3. Now let's shift one more. Okay. Because we still have an overlap. So here you get 3 minus k. h3 minus k. 1, 2, 3. Here I have 1, 2, and 3. And then we still copy. Here you can see that I have values here. 1 and 3 over 2. So the output, this output at x, xk, h3 minus k, 0, 1, 2, and maybe 3. Then we have 1 times 1, I have 1. 1 times 3 over 2, 3 over 2. So this is 1, this is 3 over 2. Then you sum over k, you get y3. That's 5 over 2. Last step, during the break, you can do it by yourself. Okay, try to do it by yourself. When n equals 4, they still shift to the right by 1 unit. Then what is y4? Okay, let's take a break. Right, so when n equals 4, okay, you shift again. So the only overlap is at k equals 2. So your output at 4 is 3/2. You can shift one more when n equals 5. Then there's no overlap. So overall, there'll be 0. So at the end, you can see that your output y will look like this. We have a values from 0 to 4. Okay. This is the case for discrete time convolution. Right. Let's see the continuous time convolution. Exactly the same procedure. You flip, shift, multiplying, and do the sum. Well, for the continuous time, you do the integration. So the convolution for continuous time is here. Okay. So again, that you shift, you flipped and shift, you times together, and then you do the integration. For example, if I have two signals, two rectangular pulse. So if it is a rectangular pulse, okay, here's 0, 2, and the magnitude is 2. And then for h, 0, here's 1, but the height is 3. So first we need to rewrite the function the signal as a function of tau rather than a t. So we have x tau and h tau. Actually, you just rewrite that the index. Okay, so we need to change this to tau. So x tau, here's tau. H tau, this is tau. Now, flip one signal, just one of the signals around t equals 0, because I need to flip. Which one would you like to flip? Because here you can also write it down as x. Well, either I flip h or I flip x. Okay, so to get either x of minus tau or h of minus tau. So that's just flipped h. That means, but for the h, we have h of minus tau, and then this is minus 1, 0, and the magnitude is still 3. Which one would you like to flip, actually? You can do whatever you want, but normally we love to flip the easier one, which means that I have a shorter signal. So it should be easier to flip the shorter signal. Next, we could find the edges of the flipped signal. If I flip it, now I need to find the left hand edge and also the right hand edge. So in this case, just copy. So this one is tau left, and this one is tau right. So here we have tau left, tau left and tau right. We flip and then we need to shift. Okay, so we shift this by an arbitrary value of t to get h of t minus tau. And then we need to get its edges. So we need to flip and then we'll shift to the right and also shift to the left. Okay, so I need to find the left hand edge and also the right hand edge. For example, if this t is negative, so say t equals minus 2, for t is minus 2. If t is minus 2, I shift to the right or left. So if I shift to the left, then my plot is, so here's tau. This is h t minus tau, and this is h2 minus 2 minus tau. So the plot is, we have 3. So what is this point and here? If I shift to the left by 2, this minus 1 will become minus 3. And here is minus 2. And actually this point, okay, for this point, that is tau left and t. So it should be t plus tau left, which is t. The tau left in this example is minus 1. So here tau left at t minus 2, this is minus 2 minus 1. So that's why we have minus 3. And this point, we have tau right and the time, that's t plus tau right. Here is t plus 0. Okay, in this case, t is tau right is 0. So tau right minus 2 will be minus 2 plus 0. So this is tau left and time. So it's t plus tau left. Here's a tau right time, that'll be t plus tau right. Let's see when when t is greater than 0, say t equals 2. So for t equals 2, then I shift to the right. Here I have tau, it's h t minus tau, that is 2 minus tau. Okay, and then the plot should be, this is still 3. And how about this point? if t is 2. So here from -1, you plus 2, so you get 1. So this is 1 and 2. And you can also say that this point is tau left t as t plus tau left. Now t is 2, so 2. Now tau left is -1, so it's t minus 1. So when we have t equals 2, we have 2 minus 1. That's why we have 1. And for this point, tau right and shift t, that be t plus tau right, which is in this case t plus 0. So when this shift is by 2, we have 2 plus 0. Alright, that's the case for t less than 0 or greater than 0. How about just have a arbitrary shift by t? For arbitrary shift by t. So if I shift just by t, suppose it looks like how do you express these 2 points? Here, because we have a specific t, so we know it is -3, -2, or even 1, 2. But if I just shift by t, I'm still using this. So for this point, that's tau left t, that's t plus tau left, so it should be t minus 1. So here we have t minus 1. And for this point, tau right t, that's t plus tau right, so it's t plus 0. So here it should be t. In this case, you can see that the signal I flipped is finite duration. What if we are not that lucky? The x is exponential, the h is, or maybe this, exponential. So it looks like there's no like ending point. Then what should we do here? So if the signal you flip is not finite duration, then one or both of the tau left t and tau right t will be infinite. That means the tau left t is minus infinity and tau right t will be infinity. It could be and or depends on your signal. Now where are we now? We just flip, we choose a signal, and then we flipped, and then we shift. Now we need to find the multiplication, which means finding the overlap. So let's find the regions of tau overlap, because when you have overlap, then you have values, otherwise you get 0. So first you can find the intervals of t, over which this product has a signal mathematical form in terms of tau. And then in each region, you just find the interval of t that makes the identified overlap happen. Okay, so for example, with no tau overlap, when t is less than 0, that's from 0 to 2. Okay, so here 2, and then we have 0, and this is 2. So we flipped h. So here we have h. This is h of t minus tau. So t is arbitrary. We can assume a here. Oh, first this is 3. Okay. And then this is tau LT. That's t minus 1. And here tau right t, that is t. If there's no overlap, t is less than 0. Okay, when t is less than 0, nothing. So we have a conclusion, which means actually when t is less than 0, that means the right side, this tau should be 0. Should be less than 0, right? With no overlap. If this t is 1 here, then we have overlap. So we don't want the overlap, so we want the tau right time, this is less than 0. So your t is less than 0. Then they just flip and then go to the right. So they go to the right, go to the right, go to the right, and finally we have a partial tau overlap. So when we have a partial tau overlap, that means like this, part of the signals overlap. Okay, so when we overlap, this is h. H of t minus tau, and here we have t minus 1, and here's t. So when t is between 0 and 1, then we have an overlap. So that means here we want this tau left t less than or equal to 0, which means your t minus 1 is less than or equal to 0. So your t is less than or equal to 1. And here we want tau right t is greater than or equal to 0. So that means t should be greater than or equal to 0. And that's why with a partial overlap, t should be between 0 and 1. So they'll continue, they're still moving. Then when they move, we may have like a total overlap, the total tau overlap, which happens in the t between 1 and 2. Let's see why. So again, we have now the total overlap means that my h, this signal, is inside the x. So suppose your h is t minus tau. Okay, and then total overlap you have. So total overlap means this is still 3. This point should be greater than 0, and this point should be less than 2. Right. This is still t minus 1 and t. And for this point, we want the tau left t is greater than 0, which means t minus 1 is greater than 0. So t is greater than 1. And here we want the tau right t, this shift should be less than or equal to 2. So that means t is less than or equal to 2. So t is between 1 and 2. Alright, so they will move on, still shift to the right. So moving. Then we have a partial tau overlap again. Okay, which means this. Okay, I only have a partial overlap. So next, partial overlap. Let's plot h. The altitude, the magnitude is still 3. And then here's t minus 1, and here's t. So this means that, what is the condition? The tau left t, what's the condition here? To have a partial overlap, this point should be less than 2, right? Otherwise there's no overlap. So here it is less than or equal to 2, which means t minus 1 is less than or equal to 2. So t should be less than 3. On the other hand, here we want the tau right time. In this case, this point should be what? What's the relation? This point should be greater than 2, right? Otherwise, you have a total overlap. So this should be greater than 2, which means t is greater than 2. So that's why t is between 2 and 3. Okay, and next, they are still moving to the right. Copy. Then there's no overlap again. Paste. Okay. That means here's h, t minus tau, and then no overlap. So the figure should be, here is still 3, and this is still t minus 1 and a t. Okay, what conditions here? We want tau left t should be what? This point should be greater than 2. Right? So we don't have an overlap. So it should be greater than 2. That means t minus 1 is greater than 2. So t should be greater than 3. That's why if you don't have overlap, t should be greater than 3. Okay, and since it is a continuous case, okay, regions should be continuous without with no gaps. So when we move the h, so no overlap, no overlap, no overlap, until we have partial overlap, and then total overlap, and then moving on, they have a partial overlap until you have no overlap, then you are done. Then you can find the product, okay, and also integrate it. So you form the product, then you find the limit of integration, and then you integrate that. So for example, when t is less than 0, your product is y equals x tau ht minus tau d tau. Your product is 0, right? Because there's no overlap. So here is 0 d tau. That's 0. For all t, the time is less than 0. Now for the region 2, let's go back to see region 2. Here we have a partial overlap. So partial overlap, how do we integrate that? We always integrate x tau h t minus tau, right? D tau. And how about the lower bound and upper bound? Where's our overlap? Here. Right. So the lower bound and upper bound should be 0 and t. So here y of t is from 0 to t. And then you have a product 2 times 3, that's 6 d tau. So it'll be 6 tau, and then tau is from 0 to t. So you get 6t. And then this t is between 0 and 1. Next, the region 3, that's total overlap. So for total overlap, this is still 6 tau. Okay, but how do we put the lower bound and upper bound? In this case, the region 3, let's go to region 3. Okay, in this case, what's the lower bound and upper bound? Yeah, so here the upper bound and lower bound should be t minus 1 to t. So here we have 6t minus 6t minus 1. So it's 6. So this is for t is between 1 and 2. Now we have a partial overlap. So here 6d tau. Again, what is the lower bound and upper bound? Region 4. Go back to region 4. So what is your upper bound and lower bound? Okay. Very good. Here is t minus 1 to 2. So we have minus 6t plus 18. This is for t between 2 and 3. And the last one, okay, so here we don't have overlap, so actually this is 0, right? We don't need to put whatever here because it is 0 for all t is greater than 3. Alright, so finally we have the value, then we can plot the figure here. So assemble the output from the output time sections for all the regions here. Okay, we have a 0 and 60, 6, minus 60 plus 18, something like that, like a trapezoid. Okay, so let's see. Here we have t, and this is y of t. We have a 0, 1, 2, and 3. So in region 1, here is region 1 when t is less than 0. Okay, yt is 0. So good, here is just 0. Region 2, what is region 2? Go back to check, go back your notes, and you'll see that it is from the t is between 0 and 1. So here is region 2. And your y is 60. So 60 is a straight line. No, it's just a line to here. Suppose this is 6. Now, when t is between 1 and 2, that's a region 3. So y is 6. So here we don't change, just a line. Okay, next, here we have a region 4. So the y is minus 60 plus 18. So when t equals 3, that's 0. So they will go back to 0. And the region 5, no overlap, that's 0. Okay, any questions for this? That's the continuous case. All right, so this is the steps for the graphical convolution. So you can also write the code and run it. So for example, so this is signal X and also the H. They are the same rectangular pulse, but this is from the exactly the same two rectangular pulses. So how do you do the convolution? Well, you flip one and then moving to the right. Okay. Or and you can see that if you have two exactly the same rectangular pulse, what is your output? You see, the output will be a triangle pulse. Okay. Now, if you have different length of the rectangular pulse, let's see. This is X, and here's H. Then you'll see that the result will be the trapezoid. Okay, why do I have like this flat one? Because one is smaller than the other one, so we have a lot of times having the total overlap, right? This is discrete time. We can do triangle pulse and rectangular pulse. So this is triangle and rectangular. Let's see. Okay, you see that we flip the easier one, the rectangular pulse. Okay, so when we move, then we have a result. We have a multiplication. Now let's see. the continuous case. Okay, here we have two rectangular poles with different width. So with a different width, you can expect what's the result. The shape should be what? Again, trapezoid. Right, and you can see that when you have the top, when you have the top, one is just all inside the other signals. Okay, and now let's see another one. One triangle pause and the other one is rectangular pause. All right, so any questions about this? The last hour we're going to talk about the system properties, especially for the linear time invariant system properties. Okay, let's take a break. All right, so now let's see the LTI system properties. Okay, for the LTI system, we can write the output as the convolution of your input and the system. Okay, this is for discrete time case, and this is for continuous time case. You flip, shift, multiplication, do the sum. Okay, and then what is HT, for example, here? That is the output. What's the output? When your input is an impulse, then I will get the output is just HT. That's the impulse response. So first, let's see the property. Property 1. If I have an input X, and then I send it to the system H, and then here we have our output. Then this output, well, in this case, we have the same output as we switch the X and H. So we can have H as our input, and then I send it to the system X. I will also get the output Y and Y. Why they have the same output? I just switch the input and also the system, because the convolution is commutative. Which means X convolve H is equal to H convolved X. So that's why that if you switch, it doesn't matter. Pretty straightforward, right? Number 2, if I send the input to two different systems, first I send it to H1, and then I also send it to H2, and then I add them together to get the output. So here's our output, AYT. This structure, we have the same output, has the same output as f(x) and then send it to a system, a bigger system, that's H1 plus H2. Also, why they have the same output? Think about the convolution again. Convolution is commutative, so they switch the input and system, they have the same output. And then convolution is distributive. Which means that X convolved H1t plus H2t. This is equal to X convolved H1 first. Oh no. Convolve H1 first, and then I have X convolve H2, and then I sum them together. This is here, and this is here. Alright, next property. If I have two inputs, X1, and I send it to the system H, I also have another input X2. I also send it to the same system okay, and then from both outputs I just add them together and I get the output. This output, well, in this case we also have the same output, so it has the same output as I just combine the input first and then send it to the system H. In this case we also get the output Y, because that for the first one this output is X1 convolved H plus X2 convolved H, and then the right hand side, that's X1 plus X2 convolved H. Alright, next. Let's have a two system and they cascade. So X go to H1 first, the first system, and then they go to the second system. And then I have an output, and this will also gives the same output as the input X. You go to just one system. This is H1 convolved H2. This is the whole system. Okay, you will also get Y. Again, why it works? Because for the convolution, it is associative. Okay, so x convolve h1, and then, well, from here, x convolve h1 first, right? And this is an input if we see the system 2. Then we convolve h2. But we can also, because convolution is associative, so I can also say that this is x convolved h1 convolve h2. So we do it first, and we convolve. And this also gives us the same output as, let's write one more. X convolved h2 convolve h1. Okay, in this case, we also have the same output as the x goes to h2 convolved h1 is y. So that means x go to h2 first, go to system 2 first, and then go to system 1. Only when the system is linear time invariant, okay, so you can switch. Remember last week, if you switch two systems, you get a different result, because first time you have time delay, and then you get the compression, or you do the compression and then you have time delay. They have a different output because that system is not linear time invariant. Okay, so this example tells us that the order of the LTI system especially in cascade doesn't matter. But in general, we don't know. Okay. In general, not true. Just like what we saw last week. Next property. If the linear time and linear time invariant system is memoryless, what does that mean, memoryless? Your output depends on what? Only the present, the current state, right? That's memoryless. Okay. So if LTI system is memoryless, then the unit impulse response can be written here for the discrete time and also continuous time. Okay, why can we write like that? Remember that for your output, the output depends only on the current input for memoryless. So the y depends on x n. So in this case, h m minus k is 0 for all the k is not equal to n. So h n is 0 for all n is not 0. So here's the corollary, just what we have here. Okay, so y n is k times delta n, or we say that for continuous time, y is equal to k delta t. This is for memoryless LTI system. Also, that means if the HN of the system, if this is not 0, when n is not equal to 0, then the system has memory. That's just the case if the LTI system is memoryless. How do you express your impulse response? Next, if an LTI system happens to be invertible, then its inverse is also invertible. Okay, here's a corollary. If an invertible LTI system with impulse and the inverse system with impulse, this one, then these two impulse systems, when they do the convolution, you will get the impulse with you will get the impulse, the unit impulse. Let's see. Suppose the x, I send it to an invertible system. In this case, that means here invertible system, and then send it to the inverse system. Then you'll get your x original signal back. So for LTI system, x, I send it to h, and suppose we have the inverse system with an impulse response, that's h bar. I should get x back. So that means x convolved h, and then convolved h bar, it should be x. So x, send it to the system, h convolve h bar. The output should be x. So that means h convolve h bar should be what? The impulse signal, right? Because x convolve h impulse, unit impulse is still x. Oh, maybe because x convolve unit impulse, you'll still get x. So let's see this example. I have a time delay system. The output is a time delay by t naught. Okay, so this is the output. Then we know that we can also express the output as the input convolved your system. So your h should be what? The delta, the shifted impulse signal. Okay, so the inverse system let's write it down. Y inverse, it should be x t plus t naught. Shift to the left. So the system response is delta t plus t naught. Then we need to check h convolved h bar. Is this correct? Let's see what is h. The delta function shift to the right by t naught, and h bar delta function shift to the left by t naught. So we have t minus t naught convolved delta function shift to the left by t naught. Tau minus t naught, and here delta tau t minus, here we should have minus tau plus t naught d tau. This is the same, right? Here I flipped and I shift. So that's changing variables. Let's have tau lambda equals tau minus t naught. So d lambda will be equal to d tau. So we have delta lambda and then delta t minus lambda d lambda. So this is delta lambda and delta t minus lambda when lambda equals 0. So this is just the unit impulse. This system is invertible. Any questions? Two more properties. We talk about the LTI system if they are memoryless, invertible. Next, let's see the causal LTI system. Okay. So what does that mean if the system is causal? So the output only depends on the current and also past input, right? So here the output depends on xt, and this t is less than or equal to t naught. So if the LTI system is causal, that means my system response is 0 when t n 0 for discrete time. For continuous time, t is less than 0. Why? Let's see. For the discrete time case, okay, this is the this is the output. Okay, we do the convolution. Okay, let's see when is h m minus k. This is 0 when k is greater than n. So h of n is 0. This is the discrete time case. Similarly for continuous time. Last one, we need to check if the system is stable or not. For discrete time, that means this is finite. And for continuous time, the integration of this system's response is also finite. Okay, so let's prove why we say that if you can find that this is finite, then the system is stable. If I have the xn for discrete time, this is bounded. So finite also means bounded. Then the magnitude. Okay, suppose since it is bounded, the magnitude is less than b for all n. Then your y is the magnitude. So here is summation k from minus infinity to infinity. X k n h n minus k. Okay, the convolution is commutative, so we can also write it down. This is k. Here we have hk. So instead of flipped the system response, we flipped the signal. So x m minus k. Right, this will be less than. We do the summation, and finally we take the magnitude. So this value should be less than. I take the magnitude first every time and then do the summation. So we just put the magnitude inside the summation. This should be larger. H k x m minus k. Okay, and then this magnitude we can take the magnitude individually. And we know that x is bounded. So here, this should be less than h. Here's bounded b. So since it is bounded, well, we want this term is less than infinity, which means it is bounded. Overall, it is bounded. So in this case, we want this is less than infinity if and only if this summation is bounded. So we can use if and only if the summation for all the sum of the magnitude of the system response, it is bounded. This also imply, okay, here, if y is stable, then this magnitude must be finite. So bounded input will have bounded output. Last, by your intuition, if I give you x, then what is x of a minus t? For x of a minus t, how do you do it? You shift by a and then flip, or you flip first, then shift by a. Or you think it doesn't matter. 3 options. 1, shift by a and then flip. 2, flip first and then shift by a. Or the third one, it doesn't matter. Okay, let's see. If I shift by a and then flip x of t, and I shift by a, that means it is x t minus a. Right, so suppose I have a signal, this is xt, 0 and 1. So if I have a signal like this, and here the magnitude is 1. I shift by 3, for example. So if I shift by 3 to the right, x t minus 3. If I shift by 3, then I should have 3 and 4, right? Okay, and here. Okay, this is still 1. And then I flip. So when I flip, there will be minus 3 and minus 4. This is 1. Okay. And then if I flip first, then shift. So again, this is the same. If I flip, then I'll get x minus t, 0 and minus 1. This is 1. And then I shift by a, shift by 3. Here, yes, shift by 3. So if I shift by 3, again, still I want to shift to the right. So if I shift to the right, then I have 2 and 3. Okay, so now let's see. So suppose this is 3. Okay, 3 minus t. which one is x of 3 minus t? This one or this one? When t equals 0, then I have x. When t equals 0, x of 3, nothing. When t equals 3, x 0. Which one? The first, if I flip, if I shift by a and then flip, when I flip, I only flip t. So here we have minus t and minus a. So apparently this is not x a minus t. So it is not equal. So this is x minus t minus 3. And the second, when I flip and then shift, actually this is x t minus a. I flip. So this is x a minus t. So this is x minus t minus 3. You see that I flip already and then shift. When I shift, I need to put this minus here again, and overall I shift here to the right. So overall you can see that if I have x minus t plus 3, this time this plus means that shift to the right. But xt minus 3 means shift to the right. But if I have that minus here, this minus becomes like a shift to the left. Okay, so be careful that if you try to plot x a minus t, that means you need to flip first, then you shift.